To continue with my earlier lecture, I would show you what it takes for slip casting. Here you see a bucket which is being stirred. It has a suspension. I will come to the details later, but this is just to explain to you why I require different types of processing aids. So, here is a bucket which they have kept, they have stirred it, and now what they will do is first sieve it. They are sieving the suspension so that the coarse particles are kept away. So, this is the sieved powder, the coarse particles have been taken out. Yes, this is the, so the sieve is taken off. Now, these are the molds which are basically the porous molds I talked of, and they are pouring the slip over there. This mold is filled up, this mold is filled up, and then they are being allowed to stand over here. What happens thereafter is, after a certain length of time, he takes a mold and drains the excess liquid. It is during this time, all this time of standing, the suspension has to stay stable. That is, the viscosity of suspension, nothing can change, because otherwise the slips property would change and the amount of slip sticking to the surface would vary from place to place, especially if the powder has fallen down, if it is a segregated at the bottom, the top part of the slip which would be forming on the wall over here, that would be very thin. Here see how the inside of the mold looks like. He is pouring out the third mold over here. And they are being allowed to dry by an airflow. Look at what happens thereafter. He is taking out each of these containers from that. The last one is yet to be taken out. So, here is the basic process where the three different materials are generated, and finally, we get these three containers by slip casting. Now, this is the way our commodes, our wash basins are made. I will take this up subject in detail later, but I brought this in to tell you that why do we add different binders. For example, I have already talked of deflocculants, surfactants which help keep the particles in suspension. The other thing that is very important is anti-foaming agents. Anti-foaming agents. Now, these antifoaming agents are very important because otherwise bubbles would have formed inside the slip. This foam is due to the gas trapped while pouring or stirring. So, what is required is a material which reduces the surface tension, so that if there are gas bubbles somewhere, they would rise to the surface and help the slip stay free of any bubbles inside. Commercial ones include dimethyl silicones. Fluorocarbons were used once, but not today. High molecular weight alcohols like say glycol, calcium or aluminium stearates are also useful antifoaming agents. So, in this particular method, we have used different materials like binders, flocculants, surfactants, mold release agents, and all of that. Having said that, let me move on to now certain processes again, like say let me say doctor blading. This process is used for making thin ceramic tapes. Like let us say tapes of barium titanate. Now, I am taking this doctor blade at this point of time very, very deliberately, because in doctor blade process what happens is we are forced to use non-aqueous media, and hence I have been talking of doctor blade of aqueous solvents so long, but now I am compelled to talk of non-aqueous solvents. So, if I am using barium titanate for making thin ceramic tapes, what will I do? First is 1 slurry of say barium titanate in a solvent. Now, because I have said barium titanate reacts with water, essentially I cannot use water. The solvent here is MEK, methyl ethyl ketone, ethanol, 50:50 volume ratio. This is the solvent. What is the deflocculant? Well, the ideal one no longer available due to European ban on fishing Manhattan fish. It is completely banned. You cannot have this fish at all. Was Manhattan fish oil. This was the ideal one and it's no longer available. Today, instead of Manhattan fish oil, we use a lot of other dispersants. We even try cod liver oil. We try the best one I try is cod liver oil. Let me say it straight, bluntly. Then for the plasticizer, since it's a non-aqueous media, I use butyl benzyl phthalate. At times I use PEG or polyethylene glycol also. As a binder, I use acryloid and acrylic, and 5 as a homogenizer, I use cyclohexanone. So to make the slurry in a non-aqueous media, these are the different types of processing aids I have to use. Let me take you through this process so that you know exactly how they are used. It is just not that they are mixed everything. So, the very first step to make slurry, of barium titanate in MEK ethyl alcohol water mixture, I would take the powder, add half of the binder, or rather I would rather add the deflocculant over here and ball mill. I had showed you ball mills much earlier, and this is in presence of the MEK ethyl alcohol solvent. I would ball mill. The ball milling here is a low speed one. It has got two functions. One is to break up the agglomerates in the powder to its finest size, and second, to see to it that the deflocculant gets attached to the powder to the maximum extent it can. In the second step, to this I would add half the binder and ball mill again. Why half the binder? I could have added the full binder, but no, I added only half the binder plus the plasticizer. This is because the binder and the plasticizer, they get dispersed throughout the solvent properly. In the third step, I would add rest of the binder plus the homogenizer and ball mill all over again. Now, let us put some times. Here, I would do a 12-hour ball mill. This one would go up from 12 to 24 hours. This one would be around 12 hours. If I am looking at the amounts, then barium titanate, if it is 100 gram, the MEK ETOH would be 20 grams. The deflocculant would be about 1 gram. The plasticizers would be about 4 to 6 grams. The binder would be about 12 to 14 grams, and the homogenizer would be around 1 gram at most. Would be 1 gram at most. Now, during this ball milling process, as I said, the deflocculant, first the ball milling helps in breaking the powders, the hard agglomerates into soft agglomerates. The deflocculant helps the powder to get suspended properly, dispersed. The binder and the plasticizer, they are the binding agents. The homogenizer ensures that I have got a very smooth, uniform suspension. To this, I may add anti-foaming agents over here and ball mill. At this particular point, what I would have is a very thick slurry, and in spite of adding the anti-foaming agents, because the balls were continuously rotating in the solvent, I would have foam over here. But they won't be too much inside. This whole thing is subjected to evacuation to remove bubbles. However, during this removal of bubbles, some solvent evaporates. So, what happens if it evaporates? Now, let us look at the doctor bleed process. Let me use this as a template for making the doctor blade. Okay. In the doctor blade, what we have is a very, very sharp edge, a very sharp edge. This is the entire template, and we have a very sharp edge whose distance from this particular plate, if this is a sharp edge, whose distance from this plate can be varied from say 0.05 millimeter to 2 millimeters, 3 millimeters. Now, in a very, very simplistic fashion, what doctor bleeding means is I have held this edge over here, the slurry which I have made is poured out here, and this edge is moved at a constant speed. What happens? As the edge moves, the slurry comes out through the bottom part, coating this area. So what happens as I keep on moving this edge, more and more of this surface gets coated. And I keep on doing that until I have moved the entire plate. Now, you have to realize, during this entire process of movement of the blade over this surface and the slurry coating this part as a blade moves along, if this is a surface, this is the blade, and the blade is moving in this fashion. Here, the slurry is rolling out, forming a thin coating out here. Over here, this is a blade, remember. Over here, at this particular one, as it moves, there will be a lot of shearing forces. As a result, there will be turbulence, and one has to add the additives in such a fashion that this turbulence does not lead to bubble formation. So, after this doctor blade process is over, that is after the entire surface has been covered, what we have is now basically the substrate, and the green ceramic tape. What we do with this, how we burn it, will be picked up later. But now you realize that how important it is to control or to choose the additives which are used in these tape casting, slip casting process, where the suspension has to remain stable. The powders cannot fall down, because then the uniformity would be totally lost. And one has to really, most cases, we can make an educated guess as to what we will do, which type of material to choose when I am doing this tape casting. This I brought in because, as I had stated earlier at the start of the lecture, when I am talking of aqueous media, it is one type of binder. But when I am talking of non-aqueous media, the type of binder totally changes. Here I have used methyl ethyl ketone and I used fish oil. But what happens if I do not have fish oil? Say the same barium titanate, fish oil is not available as a deflocculant, even though it would have been the best. What do? Do we use, what is the deflocculant that we use? That has become a major problem. And so today, people are working on trying to develop aqueous systems for tape casting of barium titanate. Now, barium titanate is but one example. There are other examples of tape of being used. Now, let me see if I can get you something on. I don't think you have got much on Dr. Blade tape casting. Let me try tape casting. No, I don't have anything on Dr. Blade tape casting. Now, let me see what would I have done if I had an aqueous media to work with in Dr. Blade tape casting. Let us take the example of which one should I take? Let us say alumina. Alumina is something that can be used for many substrates. Thick film alumina sheets are used for a lot of structures. There the system is water. So, what are the additives? I want to fabricate Al2O3 tapes. Powder is alumina, Al2O3. Over there, one of the biggest problems of alumina is this, that I had shown you earlier, uncontrolled grain growth can occur, which says that I start off with alumina powders, reasonably uniform shape, sizes, everything, and then I heat it. What I get is grains of different sizes. Now, this is something that I never want. So, in alumina what is added is grain growth inhibitor, which is magnesium oxide. What does MgO do? MgO sits between the particles of alumina and prevents grain growth. Because MgO forms MgAl2O4. If I magnify this area, let us say I have got these large grains, and the MgAl2O4 is sitting out here, it is sitting out here, it is sitting out here, it is sitting out here. It will not allow the grain to grow larger, simply because it prevents a phase boundary for the particle size to increase. Now, this is a crude example, a crude drawing, but that is how MgAl2O4 works. Other than, I brought this in because of this very particular material, that grain growth. If I am using an aqueous media, my deflocculant would be a DuPont product MFOS. This is available commercially, and it can be. Some people, I am also using CTAB. This is also very much useful in acting as a deflocculant. The binder, I could use PVA, I could use PVB, which is a polyvinyl butyral. Plasticizer would be polyethylene glycol and octyl phthalate. And the solvent can be obviously water. People have used solvents like trichloroethylene, and ethyl alcohol. This is indeed tragic, because after benzene, trichloroethylene is one of the worst known carcinogens or cancer causing to humans. Let me say how unthinking we are. We use, a lot of you have seen the whitening fluid used to whiten typewritten stuff. There is a typewritten stuff, you have made a mistake, okay, use a whiter fluid. What is the solvent? The solvent is trichloroethylene. This is a banned product for use for humans across US, Europe, Japan, and yet in our country we use it for, be used by stenos and yes, by industry. However, this one has to move away, and one has to have systems where aqueous media can be used. I do admit that in books you will not get any reference to any aqueous systems for, say, tape casting, simply because it is a proprietary item and the most industries are not ready to divulge it. There might be some papers which you have to look at. I could have given you examples of aqueous systems, say for barium titanate. But then I would be prosecuted for every violation of intellectual property right, be it the Copyright Act, be it the Patent Act, whatever. And I cannot in this lecture tell you what are the binders, deflocculants, those things that are there, that are being used by industries in the West as they move away from organic to aqueous systems. This about covers what I had planned today to talk of the different things that are used in ceramic processing. The additives. However, let me carry on to say in some cases what are the different additives that are added. It goes beyond books, is mostly not there in books. So let me talk of it in a hand waving fashion, and due to copyright and intellectual property rights, I cannot, however, show it on the screen. You see, today we are traveling faster and faster. Today the ramjet, which can fly at speeds up to 10,000 kilometers per hour in the stratosphere, is a reality. It takes you across the world in 2.5 hours. In whatever aircraft you are flying, there has to be a turbine, a jet engine like turbine. And as the speed of the aircraft increases, the strength of the jet engine turbine blades, the shafts, they have to be much higher than what is available. Different space agencies, different defense organizations have been really looking hard at how to make these turbine blades more fail-safe. You see, there have been instances when the engine of an aircraft has fallen off. There are at least 3 comes to my mind, and they fell off simply because nobody had noticed that the engine cowling fixation to the wing was failing on account of creep which occurs over a length of time, because the blades are carrying the weight of that huge engine. Ceramics offers a way out so that this sort of a failure is minimized. Today, ceramic based turbines have been made. They are in prototype product delivery place, and they are made from materials like, say, silicon nitride. What is done is the silicon nitride powder is taken, shaped into the form of a turbine blade. I'll come to that in due course of time, where I'll be talking of molding. And then that turbine blade the green turbine blade, if it is put in a furnace, one of the first things that will happen is the silicon nitride would decompose and evaporate. To prevent that, what is done? If I'm a bad person at drawing, so if this is a shaft, these are the turbine blades at an angle. As I said, I'm a bad drawing person. It looks like these surfaces of the turbine blades are coated with silica sol. Before firing, before sintering, the surface of the blades are coated with a silica sol. Now, this silica sol covers each of the blades, and during heating the silica sol melts, sticks to the surface and prevents aerial oxidation of silicon nitride, which would have occurred if the silica sol would not have been used. After sintering, the silica sol is just sandblasted away. So, here I am dealing with a material which forms a coating to prevent oxidation of the heating element or the substrate or whatever. But the most important thing is this prevents the dissociation of the basic ceramic, in this case silicon nitride, so that it does not burn off to give you silicon dioxide and various nitrogen oxides. So, this is an encasing type of material. So far I have talked of pressing, compaction, whatever. Now, as a prelude to what I will be dealing with in the next class or in the future classes, is basically shape forming, where I will take this slip casting, doctor blade casting, more pressing techniques into consideration, and also injection molding, extrusion, all of this, and in each case the demand placed on the additive so that the suspension has a constant viscosity. That is very important. One area where I would like to really draw in is hot pressing. Hot pressing is done so that the sintering rate increases. And I am bringing it in to show how do lubricants work and why are they so badly needed. In a hot pressing, we have a die this is filled with powders, and the hammer is there at the top. You will say, how is it different from cold pressing? Hot pressing is required where the sintering rates under biaxial pressing or no pressing at all is very slow. So what is done is these are dies. These are heated externally. What does the heating do? As the temperature becomes high enough, this mass becomes plastic. At this point, the hammer is lowered down to the maximum extent possible. To the maximum extent possible. Now here, please remember, like in the cold pressing, I showed you that we apply stearic acid to allow fast release of the die. Here in hot pressing, how many problems are there? One, thermal expansion. Occurs. Normally these dies are graphite dies, but alumina dies are also known to be used. So this powder will tend to stick to the side walls. So powders will stick to side walls. Boron nitride is a material which was developed by Alcoa, but they did not train people properly. What happens, what is done is, before anything is poured in, a thin layer of this powder is used to so that the walls are coated with boron nitride. Why is it so important? Let's say that this graphite die, it is so hard and crystallized that it doesn't expand. But this powder which is being compacted, the material, that will expand. And in such cases, what we require is lubricants which is very stable up to even 2000 degrees centigrade, and so is boron nitride. So boron nitride is applied to the walls of the vessel. So this boron nitride is something that I talked of earlier and is a very important thing as mold release. Other than these particular materials which I have talked of as abrasion resistance and all of that, it depends on where you are looking for what you are looking for. So one has to really try out the relative compositions of the deflocculants, the binders and the plasticizers. If we are going to have a solution which can be aqueous or a non-aqueous, I don't have any issue with that. And I personally feel one has to learn by trial and error. I forgot to mention earlier that in aqueous media, we have, as I said, MFOS, MFOS PS21A, which is basically a fatty acid. The other one we have got is zonale, which is ethoxylated. People have tried with lots of things. So in today's class, to summarize, I have talked of some binders, some deflocculants, or surfactants, basically plasticizers, deflocculants, plasticizers, anti-foaming agents, homogenizers, etc. Now, let me say one thing. The industry is moving too fast, very fast. The material which is available today may not be available in 6 months' time. So, I have given you a broad range of examples of these different materials, but they may not be available all the time at every place. You will have to have a good understanding of what do binders do flocculants do, deflocculants, surfactants do, plasticizers do, anti-foaming agents do. In the next class, I shall start off with shape forming processes. I shall start off with cold isostatic pressing, go over to hot isostatic pressing, about which I had referred to very briefly, and then go over to slip casting, shape casting, and also tape casting. Thank you.